welcome. Let's look at this interesting problem here of application of first order linear differential equation using the integrating factor. It says that the current in an RL circuit containing one resistor and one indicator is given by the equation LdI over dt plus Ri equals to ET. Solve the equation for a periodic EMF of ET in equals E naught sine Wt with initial condition of that. So this means that when T is 0, I is 0. So that's what we need to know about that initial condition. So from our equation, we can divide throughout by L. We'll have di, because L is a constant and it's attached with di over the t there. Then it's going to be R over L times I equals to, instead of writing ET, I'll replace it with E naught multiplied by sine Wt. Then I will divide here by L because I'm dividing throughout by the L. So I can see that this is exactly the first order linear differential equation. We can see y is actually equal to I, and p of x it's R over L, and q of x is E naught over L sine Wt. So okay, let's find the integrating factor. And we know that when you find the integrating factor, we say I of x, but let's just say I of t now, because our operational variable is t. We know that it's going to be e to the power px dx. So what is px? It's R over L, then dt. When we solve for that, we'll find that it is actually RT over L. So that is the integrating factor, and we know that the general solution is going to be integrating factor times y. In this case, it's actually going to be times I. Then it's equal to the integral of qx. What is our qx? It's E naught over L, then sine Wt times the integrating factor, which is E to the power RT over L, then dt. We have actually here now an integration by parts integral. So we need to know how to use integration by parts. Let me write on a new page. So we have E to the power RT over L times I equals to integral of, we can also take E naught over L outside the integral. Then we'll be left with sine Wt we'll be left with sine Wt e to the power RT over L dt. So let's see something here. We know that integration by parts formula, it's actually U dV is equal to UV minus integral of V du. So in this case, we can say that U, it's actually equal to E to the power RT over L. Then du will be equal to what? R over L E to the power RT. Then we will let dV to be equal to the function of sine Wt. So this Wt, I think it's omega, but let's just use W. Then V it's going to be negative cos Wt over W. So we have solved everything that we need to plug in that formula there. So what are we having? We're going to have e to the power RT over L times I equals to my U, but I must not forget that the constant there, E naught over L. So everything should be multiplied by E naught over L. What is my U? My U is E to the power RT over L times, what is my V? It's minus cos Wt over W minus the integral. So let's write this integral here. So my integral is V du. What are the constants that are within V du? We can see that on du we have R, and then we have R over L. So on V we have W there. So it's going to be R over L. So V, it's actually a negative. So this sign will change here to be a positive. So it's going to be cos Wt. I won't divide by that W because I took it out already. Then multiply by its V du, multiply by E to the power RT over L. Now dt. So actually I can put dt there. So I still have integration by parts. So I need to now make U equals to RT over L. Then du, we have already done it on the previously. So it's RT over L dt. But now the difference is that dV, it's cos Wt over W. Then V is going to be a positive sign now. Sine Wt over W. Then now we need to go back again and substitute. So we have E to the power RT over L times I is equal to E naught over L. We are writing this term there. Let's take the negative in front. So RT over L cos Wt over W. Then plus, now we have R over LW. It's this one there. Then we will have, let's not have a square bracket inside the square bracket. Let's have a normal brackets. We'll use integration by parts again. So what is our U? We know that it's UV minus V du. So our U, it's E to the power RT over L. What is our V? It's sine Wt over W minus the integral. So again, because we will still have the integrals, the constants, we know that on V du the constants is W and R. So these constants are still the same. So it's R over LW here. And then we will have V du, we will have sine Wt, and then E to the power RT over L dt. We close this bracket within the square brackets. So now what we need to do is to multiply throughout by this. So we'll have E to the power RT over L times I equals to E naught over L, then minus E to the power RT over L cos Wt over W plus, I will multiply throughout now. I will have R E to the power RT over L sine wt over L w square, then minus r square over L square w square integral of sine wt e to the power rt over L dt. So this is a little bit long because we are not working with numbers, and this integral was alternating between sine and exponential function. So we can see that we still have that one. So we need to replace it, because initially we said that if we look at this integral here, where I used the red marker, it is equal to that. We need to make that integral subject of the formula. So we will have now the integral of sine wt e r t over L, it's over L dt, it's equal to L over E naught e to the power rt over L times I. So it's a little bit long. So we need to replace this by what we have there. And then how is it going to look like when we replace? So let's do it on a new page. We will have e to the power rt over L times I equals to e naught over L into minus e to the power rt over L. Then let me check here. Cos wt over w, it's this time there. We have managed to do that. Then this one, it's a plus. Is it a plus or a minus? It's a plus. Plus r e to the power rt over L. Is it a sine or a cos? It's a sine. It's a sine wt over L w square. L w square. So now we are going to the term that we need to replace. So we can see that the constant is r square. Let me bring it closer to the minus. So it's r square over L square w. And then now the integral we need to replace with what we used the red marker for. So we're going to have L over E naught e to the power rt over L times I. We do not have the integral anymore. We have managed to get rid of the integral. So we are almost done. When it is like this, you can start to smile. So what can I do now? I can multiply. I need to take the term with the I to the left hand side. So I can only multiply it by E naught over L. So I will have e to the power rt over L times I. Then if I do that, I will have this E naught here over L, and then multiply that term. So it's going to be r square L e to the power rt over L times I, then over L square w square E naught. And then because it's with a negative, let's just take it that side once. Let's take it to the left hand side once. Then it's going to be, let's put a plus sign there so that we can jump step, because this problem is very long. If we don't approach it smart, we'll do it the whole day. So we'll have E naught over L. I can now factor out, W on this term. I will have L W, and if I start with sine W, or I will have R over LW, sine WT times e to the power RT over L minus e to the power, let me start with the cos like I did with the sine. So I will have minus cos W2, because I factor out W, I won't have W anymore. So I will have just e to the power RT over L on that term. So it's okay, it is good enough. If we made a mistake, we will go and check. We will see at the end, because it's very long. So what we needed to do is just to factorize. So, and it's very easy to make a mistake. So we have L and L here. We have E naught and E naught. So we can cancel that. Then we are left only with e to the power RT over L times I plus R square times e to the power RT over L times I again, then over L square W square. It's equal to this term here, e to the power naught, e naught, not power naught. This will write it as it is for now. Sine WT times e to the power RT over L minus cos WT times e to the power RT over L. So, okay, we are almost done now. Let's be patient. Let's factor out e to the power RT and L. E to the power RT and I. E to the power RT over L, I. We get that as 1 over R square over L square W square. And this term here, we can rewrite it like this. Let me rewrite it like this to save time. It's gonna be L square plus R square over L square W square, just like that. I just factored out e to the power RT over L. Then we'll have E naught over L WT plus into LW sine WT times e to the power RT over L minus cos WT times e to the power RT over L. So we know that mostly when we are working with integrating factor, we say integrating factor times y equals to the integral of qx integrating factor dx. Then we solve this, then perhaps we'll get the answer to that. We know that the answer to that integral then plus c, it's going to be y equals to, so what I'm trying to say is we only add plus c before we divide by the integrating factor. So you will see the importance of that as we continue. So I can divide throughout by that, and I know that If I do that, if I do that, I need to be able to, if I divide by this, I have to multiply that on the right hand side by the inverse of that. So I will have e to the power rt over L times I is equal to, now I will have because here we have E naught and and LW, so I will have only LW, sorry, I will have E naught LW over L square W square plus R square if it goes that side. Then RT, R, just R, LW sine WT times e to the power RT over L minus cos WT, and then over L. Then from here we can write plus C. So if we have integrated to find the general solution, it is good enough to leave it there. But because we want to find the particular solution, we need to continue to find the value of C. The particular solution is I naught equals to 0. So we will then have, let's write it on the, so in the place of t we place 0, and then in the place of I we place 0, and then solve for C. Or initially, let's divide everything by e to the power RT over L times I. Then we will have I equals to E naught L W over R square plus L square W square. I have to divide it there. I will be left with only R over LW times sine WT. If I divide there, when I divide there, I'll be left with minus cos WT only if I divide by e to the power RT. And also, if I divide on the side of C, it will be e to the power negative RT over L. So that is the value of I. So with this initial condition here, we can solve for C. If we put 0 in the place of I, we will have E naught LW over R square plus L square W square. So we know that when we plug 0 in the place of sine, it's going to be 0. When we plug 0 in the place of cos, in the place of t, of cos t there, cos 0 is actually negative 1. And then we will have, cos 0 it's 1, then we have a negative, so it's going to be negative 1 there. Then we'll have C. Everything will be e to the power 0 when we plug 0 in the place of t on that exponential function. E to the power 0, it's 1, so we'll be left with C. So when we solve for C, we'll find that it is E LW over R square LW square L square W square. So now a particular solution will be like this: E naught LW R square plus L square W square, then R sine W over LW minus cos WT. Because the value of C is equal to this, we can also just factor it out as well. Then we will have only e to the power RT over L inside there. So this is the final answer. I realized that I had to omit some of the steps here because it is a very long problem, and we were not working with numbers. We were working with constants of letters R and E naught, L and W. So that was a little bit confusing with that. So thank you for watching. Please like this video and subscribe. Thank you.